Hi folks, this is Heath. We're on section 14.4 today. This is the last section before the exam. Our exam will be on Wednesday and we will review on Monday, but I want to make sure that everybody is ready before the weekend. So this is the last day of material that will be on the test. We're on the section for tangent planes and linear approximations. Let's go ahead and get started. So, reviewing a little bit from single variable calculus, when we here you go. When we wanted to find the tangent line to a curve, say we had some sort of curve here, and we wanted to find, say, a tangent line at some point. Well, it's a line. And so the equation of the tangent line was, like all lines, we could write it in the form y equals mx plus b, where m is the value of the derivative at whatever x coordinate this is. And then we could find b by plugging in x naught and y naught. So m was the slope of the tangent line, and so we could find m by finding the derivative of the original function. So that's an idea that I'm hoping everybody's very comfortable with. So let's try this example. Find the equation of the tangent line. This is a single variable calculus problem where we only have x's and y's. There's no z's. We just want to find the equation of the tangent line to this function, y equals 3x squared minus 2x, at the point 2, 8. So we take the derivative, y prime is equal to 6x minus 2. So we're at the point 2, 8. That means that x is equal to 2. And so 6 times 2 minus 2 is equal to 12 minus 2, which is 10. So that's the slope of the tangent line. Y equals 10x plus b will be the equation. So the equation is now y equals 10x plus b. But then we know that the point is still 2, 8. And so if I plug in 8 for y and 2 for x, that's 8 equals 20 plus b. And so b has to equal negative 12. And so we get y equals 10x minus 12 for the equation of the tangent line. Okay? So you've done this before. This isn't too bad. We take the derivative, we plug in the point into a derivative, we get the slope. Then once we have the slope, we plug in the point into the y equals mx plus b equation. We solve for the intercept b, and we get that. When we go from 2 dimensions to 3, our tangent is now going to be a plane instead of a single point. A plane instead of a line. So if I've got, some sort of surface here, and some point on that surface, I have an entire plane that's tangent to the surface at that point. Well, we can write the equation of a plane in the form z equals a slope in the x direction and a slope in the y direction plus b. In other words, it looks like the equation of a line, but we have an x term and a y term. We have a slope and a variable for both inputs. And these slopes correspond to the partial derivatives of the original function. And we know how to do partial derivatives now. This is something we did last time. So let's give this a try. Find the equation of the tangent plane to the hyperbolic paraboloid z equals 3x squared minus y squared at the point 2, 1, 11. Okay, So if we calculate the partial derivative of dz dx, we get 6x for the first term, and the second term goes away. And we're at the point 2, 1, 11. And so 6 times 2 is 12. And so that's the slope in the x direction. If we calculate the partial derivative with respect to y, we get the derivative is, this term goes to 0, we get negative 2y. And again, we're at the point 2, 1, 11. And so negative 2 times 1 is negative 2. And so now we know that the equation is going to be z equals 12x, the slope in the x direction, and negative 2y, the slope in the y direction, plus b. It's almost like the equation of a line with a slope in the x direction and a slope in the y direction. So now we have to plug in the point 2, 1, 11 to find b. And so 11 is z, 2 is x, and 1 is y. So this is 24 minus 2 is 22. So 11 is equal to 22 plus b. And so b will be negative 11. And so there's our final answer. Z equals 12x minus 2y minus 11. And that's the equation for this tangent plane. Okay? And I have one last thing I want to say about this example before we move on. So I'm going to copy this equation onto the next slide. 12x minus 2y minus 11. If we have to find the normal vector to the plane, the normal vector to the plane we get by taking this plane and putting it in what they call the standard form with the x and the y and the z on the same side. So we get 12x minus 2y minus z equals to positive 11. The 11 is a constant, so it goes on the other side. These are the same equations, excuse me. These are the same. I'm just rearranging the terms around, but this tells me that the normal vector is 12, negative 2, negative 1. That is, you can't look at this form of the equation and see the positive 1 times a z and say that there's a positive 1 here for the normal vector. When the x and the y and the z are all on the same side, this is the derivative dz dx. This is the derivative dz dy. But this is a negative 1 and not a positive 1. Okay? And so be careful about problems involving the normal vector. Make sure that you think about which form of the equation you want to use for this. Okay? All right. So let's try another example, a little harder example with a messier function. We're going to find the tangent plane to this surface at the origin. So we need to find the derivative of z with respect to x, and then we'll need to find the derivative of z with respect to y, these partial derivatives here. With respect to x, the derivative of x is 1, and cosine y doesn't change, so this is just going to be 1 cosine of y. And over here, the derivative of e to the x is e to the x, and y doesn't change, so this is going to be y e to the x. I'm only taking the derivative of the terms with the x in it. So then, when we take the derivative with respect to y, the derivative of cosine y is negative sine y, and nothing changes about the x. The derivative of y becomes 1, and e to the x doesn't change, so this is just 1 e to the x. All right, we have to figure out what's going on now at the origin, which is 0, 0, 0. Cosine of 0 is 1, minus 0 e to the 0. Well, that's just going to equal 1 minus 0. That's 1. This is at the origin. Negative 0 sine 0 minus e to the 0. Well, this term is 0, and e to the 0 is 1, but we're subtracting it, so this is going to be negative 1. And so now we have an equation, almost, z equals 1 times x plus negative 1 times y. X minus y plus b. So we have to figure out what b is. Well, we're at the origin. We use the origin in all three steps. So 0 equals 0 minus 0 plus b. Well, then b turns out to be 0 also. And so the tangent plane to this surface at the origin is z equals x minus y plus 0. Okay? And so the normal vector to that plane, if we needed the normal vector, is 1 in the x direction, negative 1 in the y direction, and negative 1 in the z direction. If we brought the z over here, it would be negative z. So we have the tangent plane to this surface. All right. So we're done with the big, hard topic for the day. How do we find a tangent plane? The other topics we want to talk about are just different ways of putting the tangent plane to use. The linearization of a function is the tangent plane, but it's written in the form of a function. That is, instead of z equals some slope times x plus some slope times y plus b, that's the tangent plane. We want to write this as a function. The linearization in terms of xy is m1x plus m2y plus b. We're now emphasizing that we are turning this into a function so that we have input variables x and y that generate the output. These are conceptually really close to each other. They're basically the same thing. If the tangent plane is 4x plus 2y plus z equals 11, if somebody gives us a tangent plane in this form, well, then we can find a linearization by getting the z by itself, bringing the 4x and the 2y over to the other side, and then whatever we get, that's the linearization function Lxy. Okay? So the linearization is just a different way of talking about the tangent plane. The advantage of linearization is that it emphasizes the input variables, and sometimes that's useful when we're talking about variables other than x, y, and z. If we're talking about some kind of process where we have control over the input, but we don't have control over the output, we may want to identify what those inputs are that we can control. And so using that notation instead of an output-based notation gives us a sense of sort of understanding how the process works. And we can use linearizations. What they're used for a lot of times is for working out approximations. We did a problem like this in single variable calculus, and look, we're dealing with a single variable function here. So this is a single variable example. And then we'll do a multivariable example also. So right now we know that the natural log of 3 is approximately 1.099. And we would like to estimate the natural log of 3.1. So the derivative, f prime of x, is 1 over x. And so the tangent line would be y equals, so we're at the point 3 comma natural log of 3 would be 1 over 3. So y equals 1/3 x plus b. And, well, let's see, what are we looking at here? We're still at the point 3 1/3 natural log of 3. And so we know that natural log of 3 is about 1.099 equals 1/3 x times 3 plus b. 1/3 times 3 is 1. And so b is about 0.099. And so the tangent line is y equals 1/3 x plus 0.099. The linearization would be L of x, and again we only have one variable, equals 1/3 x plus 0.099. And so now we want to find the linearization at 3.1. That's 1/3 times 3.1 plus 0.099. 1/3 times 3.1 is 1.033 plus 0.099. And that's 1.132, basically. All right. And again, this is an approximation, but this is approximately the natural log of 3.1. Okay. We calculated the derivative. We figured out what the b was in the tangent line. We found the tangent line. The linearization is the same thing, just written in the form of a function. We plugged 3.1 into that function, and we calculated a value which is approximately the natural log of 3.1. All right, so let's try a multivariable example for this. Here's a multivariable example. The volume of a cylinder is, and we're talking in this case about a circular cylinder, pi r squared h. So the volume depends on the radius and the height. Estimate the change in the volume of a 2-meter high cylinder. So we're dealing with different variables than x, y, and z in this case. The height is 2. The diameter started out at 6, but it's going to increase to 7. And so the volume in this case is going to be pi times 6 squared is 36 times 2 is 72 pi. Okay? So let's figure out what the tangent plane to this equation is here at the point from the original cylinder. It hasn't changed yet. So the derivative of v with respect to r is, take the derivative of pi r squared, we get 2 comes down, 2 pi r, and nothing happens to the h. And at the point 6 to 72 pi, that's 2 pi times 6 times 2 is 24 pi. Then we find the derivative with respect to the height. So this time the derivative of h is 1, and pi r squared doesn't change, so this is just going to be pi r squared. And at the point 6 to 72 pi, that's pi times 6 squared, or 36 pi. And so now we know that the tangent plane will have equation v equals 24 pi times r plus 36 pi times h, the slope in the r direction times r plus the slope in the h direction plus some constant b. Oh, well, we could figure out what that is by plugging in this point again at 6 to 72 pi. We get 72 pi equals 24 pi times 6 plus 36 pi times 2 plus b. And if we solve all this out, we get b equals to negative 144 pi. And so now the linearization in terms of r and h, well, it's the same thing as a tangent plane. We just write it as now a linearization function. 24 pi r plus 36 pi h minus 144 pi. So now we can use this to estimate what happens if the height remains at 2, but the volume increases to, or the radius increases to 7. So the linearization at 7, 2 is 24 pi times 7 plus 36 pi times 2 minus 144 pi. And that's, when we work all of this out, is going to be 96 pi. Well, the question, this is an estimate of the volume. Remember, we're just taking the v and replacing it with L of 7, 2. But this estimates v. The question is asking for the change in the volume. Well, if the volume was 72 pi and it's now 96 pi, then the change in the volume is just 96 pi minus 72 pi, which is 24 pi. Okay? So we've got that problem finished. A little bit of work here, but I'm hoping all of this is making sense. We find the equation of a tangent plane, which has a slope in the r direction and a slope in the h direction. So we do both partial derivatives. It also has an intercept. In this case, it's a v-intercept. So we have to plug in the point 6 to 72 pi to solve for b. And then we get b. I'm just rewriting the tangent plane now as a linearization. So this is a function. And then we plug the new cylinder in there, the one that's 7 meters in radius instead of 6 meters in radius to get a new volume. And then we figured out what the change in volume was. Okay? All right. Let's keep going. This is another way of writing the idea, what's going on here. The differentiable function, let's say we have a function that has partial derivatives everywhere. If we move from x naught, y naught to another point where this is the change in x and the change in y, then the approximately change in z is the slope in the x direction times dx plus the slope in the y direction times dy. There is no plus b here. No plus b term. Because b doesn't change. And so if we're measuring just the amount of change in z, then the b will be the same before and after. And so we're only interested in the part that changed. Okay? So the b cancels and we're just looking at the differential here. So it's almost like the linearization. Let me back up here. Back up a little bit. Well, I'm going to back up even a little bit more. Oh, right here. Where we get the partial derivative times x and a partial derivative times y, but the plus b, because there's no change in this is a constant, it's the same before and the same after. And so the only part of the linearization that changes is this part here. And so if all we're interested in measuring is change, then we don't need the b term. So the b term is gone from the differential. And it's called the total differential of f at x naught, y naught. It's the total of the change based on x and the change based on y. Okay? It is an approximation for the change in z. It's most accurate when dz and dy are both small. Okay? So let's look at an example here. Find the total differentiable of this function here as p moves from 2.3 to 2.05, 2.96. All right, wow. So we need some partial derivatives. So the derivative of f in the x direction will be 2x plus 3y. And at the point 2,3, that's 2 times 2 plus 3 times 3. That's 4 plus 9, which is 13. Then the partial derivative in the y direction is 3x minus 2y. And at the point 2,3, that's 3 times 2 minus 2 times 3, which is 0 in this case. And so the differential, dz, is 13 times x. And I'll go ahead and write plus 0y. You would normally have to write plus 0y, but I'm going to go ahead and write plus 0y. And again, we don't bother to write the b. So it's the part of the tangent plane that represents change. Okay? And we want to know what happens. My bad. Hold on. We're measuring just change. So it's just 13 times the change in x plus 0 times the change in y. I'm sorry about that. The change in z is 13 times the change in x plus 0 times the change in y. Okay? And so, in this case, the change in x is positive 0.5, positive 0.05, and the change in y is negative 0.04. It won't make any difference because we're about to multiply it by 0. But so the change in z is going to be See, 13 times 0.05 plus 0 times negative 0.04 is 0.65. Okay? So that's the change in z. All right? That's the total differential here. We're only measuring the change in the tangent plane, not the entire tangent plane when we do this. All right, the question says now to estimate f of 2.05 and 2.96. Well, f of 2.3 is not hard to calculate even without a calculator. It's 2 squared is 4. 3 times 2 times 3 is, I'll go ahead and write this out. 2 squared plus 3 times 2 times 3 minus 3 squared is 4 plus 18 minus 9, which is 13. And so f of 2.05, 2.96 is going to be approximately 13 plus the change in the z value, which is 13.65. We figured out how much the z value was going to change, and so we figured out the original z coordinate here. We used the total differential, and then we figured out how much it was going to change. Okay? There are lots of ways that we could come up with this approximation. And this is just one way of doing it. All right? Let's try another example. You're in charge of quality control for a company that makes cylindrical storage tanks. The tanks are supposed to be 25 feet high, 25 feet high, with a radius of 5 feet. And we know that the volume is pi r squared h. Which of these two dimensions is more critical if we want to minimize the variation in the volume of the tanks? Okay. Well, then let's look at some derivatives. The change in v with respect to r is 2 pi r h. And then at r is 5 and h is 25. And then the height is going to be 625 pi. Or the volume is 625 pi. So I'm using the coordinate system radius, height, volume. Then 2 pi RH is going to be 2 pi times 5 times 25, or 250 pi. All right. The change in volume with respect to height is the derivative of pi r squared h with respect to height, which is pi r squared times 1. And again, at 5 and 25 and 625 pi, we get we get pi times 5 squared, which is only 25 pi. And so the total differential, and it's not z anymore, it's the change in the volume, is 250 pi times the change in the radius plus 25 pi times the change in the height. This is the total differential. If we want to minimize the variation, we want to keep the change to be small. What I notice is that for every unit the radius changes by, the volume goes up by 10 times as much as every unit of change in the height. If the height varies by a little bit, the volume will change by 25 pi for every unit variation in height. But if the radius varies, the volume goes up by 10 times that amount, 250 pi for every unit variation in the radius. And so which direct dimension is more critical if I want to minimize the variation? I want to control the radius, because a small change in the radius will have a much bigger effect than a small change in height. And so radius is more critical. Okay? Radius is more critical. All right. In a sense, we're done. There's no more material to cover in this section. If you're following along in the notes, there's a little section at the end that says some additional examples. I'd recommend pausing the video at this point, trying to work through those problems on your own, see how far you can get through, and then if you get stuck, unpause the video. We'll work through those next 3 examples right now. Okay? So going back to what we did at the beginning, find an equation for the tangent plane to this graph here, z equals square root of y minus x at the point 1, 2, 1. So to find an equation for the tangent plane, we need the partial derivatives. So the derivative with respect to x is going to be 1/2 times y minus x to the negative 1/2 times the derivative of the inside part with respect to x, which is going to be negative 1. And at 1, 2, 1, that's going to be 1/2 times 2 minus 1 to the negative 1/2 times negative 1. 1 to any root power is just still 1, so this is going to be 1/2 times negative 1 is negative 1/2. Then the partial derivative with respect to y, almost going to be the same thing as 1/2 times y minus x to negative 1/2. But then we take the derivative of what's inside the parentheses with respect to y, and we get positive 1. And so at 1, 2, 1, we get positive 1/2 instead of negative 1/2. We don't have that negative sign that we had over here. And so the tangent plane is z is equal to 1/2 times negative 1/2 times x plus 1/2 times y plus b. Again, the tangent plane looks kind of like the equation of a line, mx plus b, but there's an mx and an my, just a slope in both directions here. And then at the point 1, 2, 1, 1 is equal to negative 1/2 times 1 plus 1/2 times 2 plus b, which is negative 1/2 plus 1 plus b. And so b has to equal to positive 1/2. And so that's our final answer. The tangent plane is z equals negative 1/2 x plus 1/2 y plus b, which is also 1/2. All right. Example 9. We are measuring the length of a long, thin rectangle. So the length is L, the width is W, the area is length times width. Which dimension should we measure more carefully? Well, the change in area with respect to length is W, and the change in area with respect to length, with respect to width this time, is equal to L. That's just, each of these is the coefficient of the other one in these cases. And so the total differential is that the change in area is W times the change in length plus L times the change in W. W times the change in length, L times the change in W. So if we are trying to calculate the area and we don't want to have an error in the answer, a small amount of error in the length gets multiplied by W, but a small amount of error in the width gets multiplied by L. And since we're told that the rectangle is long and thin, L is going to be big compared to W. W is going to be a thin rectangle, but it's going to be long. And so if the error in the length gets multiplied by W, but the error in the width gets multiplied by L, the error in the width will have a more profound change in the area than an error in the length. And so we have to measure this more critically because it gets multiplied by the larger value. And so width is more critical than length. So that's the computational answer, but we can kind of visualize this also. If I make a small error in the length, and I accidentally calculate the length as being this amount instead of this amount, then I've added this much error by mistake because I have not measured the length carefully. But if I miscalculate the width by that same amount, I'm adding all of this area to my calculation because of the error in the width. And just visually, I can see that miscalculating the width by a certain amount will add a lot more area than miscalculating the length by that same amount. And so in this case, if I want to calculate the area, I want to make sure I have this value very accurately measured, because a small change in that, the area gets multiplied all the way throughout by L. Okay? All right. So then let's do the last example that's on the handout. Number 10. Find a linearization for this function at the point 0, 0. So the partial derivative of the function with respect to x is 2x, and at the point 0, 0, that's just equal to 0. 2 times 0 equals 0. Well, the partial derivative of the function with respect to y is 2y, and at the origin, 2 times 0 is also equal to 0. And so the tangent plane looks like z equals 0x plus 0y plus b. Well, let's figure out what this b is. When in the original function, when x is 0 and y is 0, then b would be z would be 1. 0 squared plus 0 squared plus 1. So at the point 0, 0, and now we know that z is equal to 1, 1 is equal to 0x plus 0y plus 1. All right, so the linearization is just the same equation, just with the z replaced by xy. And it's just equal to 0x plus 0y plus 1. The linearization is a constant function here. Okay? Well, the function goes on and says, or the question goes on and says, what does your answer signify? What does it mean if your linearization is constant? Well, if we think about what that meant in single variable calculus, if we had a function and the tangent line had the form y equals a constant, that meant it was horizontal. And if the tangent line was horizontal, that meant the slope was 0. Not y prime is equal to constant. Y prime would be equal to 0, so that the tangent line was 0x plus a constant. Sorry about that. The slope would be 0, and that meant that we had a critical point. Could be a local minimum, but it might be a local maximum also. And if you are clever, you could even have a slope of 0 and not have a maximum or a minimum. You could have a critical point that turned out to be neither a maximum or minimum, but it was still a critical point. Same thing in this case. If I have a three-dimensional surface, but the tangent plane is perfectly level, it doesn't have a slope in the x direction and it doesn't have any slope in the y direction, then it is we're measuring the tangent plane at a critical point. And that critical point is likely to be a maximum or a minimum, but not guaranteed to be. And so this tells us, what does it signify? This signifies that 0, 0 is a critical point. Okay? All right. Have a fantastic weekend. We will review on Monday and take the test on Wednesday. See you around.